I just want to know slightly, how many of you have seen coding theory before? Okay, and say communication complexity. Okay, good. Okay, so today the thing that I will be talking about is property testing. Now, the another name for property testing is sublinear algorithms. Now, what is sublinear algorithms? Now, of course, this is not a very well specified thing, because I can talk about sublinear space, which of course is a completely different subject, like log space algorithms and something like that. But here we are more concerned about, say, time in some sense, say sublinear time. What does it mean? That we have been given a problem. We say the problem is of size n, the input size is n, and we want to have an algorithm or answer that problem in time which is much smaller than n, okay, possibly constant. That's what our hope is. Now, you must of course ask, you have been given an input of size n, and we are not even have enough time to read the whole input. So, of course, we cannot solve the problem. So, the idea is to come up with an approximate solution of that problem. Okay. So, here I use the word approximate, but please don't mistake this one with approximate algorithms. So, I will explain immediately right now what do I mean by approximate solution. So, let us take a small example. Say we have been given a graph G, okay, and now we have been asked the question that is G 3 colorable. This is a problem that most of us have seen, correct? So, in approximate algorithm that we have seen earlier, we look at the whole problem, we try to find out the chromatic number of this problem in polynomial time and such things, and that's the idea, that okay, we don't even know whether the graph can be colored in 3 colors or not, but we can at least tell you whether the graph is colored in 6 colors, if it is a too approximate thing. But here, I can't do that. I can't even look at the whole graph. So, instead I would like to say something like this, that see, you have given me a graph. If it is 3 colorable, I will tell you that okay, it is 3 colorable. But if the graph is really not 3 colorable, something like very far away from being 3 colorable, then I want to say that no, it is not 3 colorable. Okay. So, let me just write down here. So, we want to distinguish between these two cases. In the two cases, first case is that G is 3 colorable, and the other one is that it is far from 3 colorable. I have not specified the whole definition yet. I will go over some examples and then I will give you the exact definition of all of these things. But the basic idea is this, that we want to distinguish between a problem, a given input satisfying a problem or giving the correct answer, or it is far from giving this correct answer. Okay. And the idea is to look at a very small fraction of the input, ideally a constant number of bits. So, this area of research goes from, in one side it starts from, it's a very well known study in statistics, and the other side goes up to learning theory and such things. So, let us come up with this most easy algorithm that one can think of. Say, okay, so this is motivated from a real life thing. So, say in say Philips is a company that makes bulbs. So, they make lots and lots of bulbs, and they claim that say a particular kind of bulb, they last for 100 hours. Okay. Now, when they are producing it, they have to somehow make sure that the production is going on fine. Correct? I mean, there's no problem in the whole setup. So, how can they do it? They of course can test all the possible bulbs one by one. But now, bulb is something that if you test one bulb, try it out whether make it run for 100 hours, then okay, you are convinced that that particular bulb was good, but now it is useless because it has already run for 100 hours. So, you cannot actually look at all the bulbs. So, there is a whole collection of bulbs that comes in. The idea is that if you can find any bulb not good, when a bunch comes out, if you find a bulb which is not good in that bunch, you completely discard that bunch. Like, okay, I have found out that this machine has not solved. But it's possible that, I mean, in the whole bunch, one bulb is bad or something, and I cannot find it. So, what I want to try to say is that, so I will try to model it in terms of math. Okay. So, I have these bulbs B1 to say Bn. Now, if a bulb is good, I number it 1. I mean, I now don't number it, but it's like if a bulb is good, it is 1. If a bulb is not good, it is 0. Okay, so it's 0 and 1, each of them. So, if bulb is good, it is 1. Okay. So, I want to distinguish between the two cases. If all the bulbs are good, that means if all of them are 1, so if for all I say Bi equals to 1, then I want to let that bunch go through. So, then I want an algorithm that will accept. And okay, I cannot say that if one bulb in the whole thing is bad, then what can I do? Because it's not possible for me to check it. But the idea is that if a lot of them are bad, I want to discard that bunch. So, if a lot of the bulbs are bad, then I want to reject. So, it is exactly in the way in this theme of what I wrote there. If it has a property which is if the string is all 1, then I accept. If the string is far from being all 1, it is reject. Okay. So, can someone come up with some?
There are some cases where you don't tell anything.
Yes, in the middle cases, it might be that I of course don't want to look at all the bulbs, correct? I would hope to look at only say 3 bulbs in 100 bulbs or something. And then I want to say with confidence that 99% of the bulbs are good. With 99% probability, I can guarantee you that it is good. Okay. So, of course, there is some probability of my algorithm not working, but there is a very low probability. So if the bulb is, so what I want to say is that, yeah, so if the number of bulbs that are bad is very small, it is fine I make a mistake. If the number of bulbs that is very bad, that are bad is a large number, then with high probability I want to catch that. So let's say I just formulate it here. So if it is all 1s, then I accept. If the number of 1s for which it is 0, so basically number of I such that Bi is equals to 0, if this number is bigger than say a constant fraction, I don't know, say 0.001 times n, then I want to reject. Okay. And of course, you can convince yourself that even if I ask you to do this one with 100% probability, with one probability 1, you will not be able to do it unless you go through the whole thing. So in both of them, we want to, instead of saying accept and reject, let me just write it down. So I would like to say that I want to come up with an algorithm A such that if this is the case, then probability that A accepts is bigger than 1 minus some delta. Say in this case, let me just write down, is greater than 0.99. And in this case, the probability that A rejects is also 0.99. So this is the this is problem clear. So now can someone give me an solution to this problem? What will you have done? I mean, I can phrase it in n number of different ways. One easy way is that when you were in school, you used to get these books, correct? Like every year the edition used to change. And it was never clear to me that whether the two books of two editions are actually different or they are just same with a different edition. The question is that do I need to buy a new book or not? How did we check that time? We cannot go through the whole book, correct? We have to do some kind of a. Exactly. So this exactly what we have to do. We have to randomly sample here. Open to a page and look, see whether that page number is, or that page content is same as the same corresponding page number there or not. It's exactly here. It's a random sample. So if I just pick a random bulb and see whether that bulb is good or not. Now, if the bulb is good, then I say that okay, good, the bunch is good. So in the whole bunch, I've just looked at only one bulb. Okay. Now what can we say here? Let's see. Let's analyze this problem here. If all the bulbs are good, I will accept for 100% probability, correct? Because in no way I'm rejecting. Because whatever bulb I pick, it will be good. So it will not even be one, it will be this. In fact, it will be exactly equal to be 1. What happens here? So epsilon fraction of the bulbs are bad. Okay, I randomly pick one of them. So what is the probability that I have picked up a bad bulb? Epsilon. Sorry, it's like this epsilon fraction of them. So it's like this by n. You're right. So which is basically epsilon. So in this case, the probability in that case I reject is 0.001. Okay, that's of course not good, you can say. So I have an algorithm that if it is all good, I accept with probability 1. If it is, if some of them is bad, then I will catch that one with some very small probability. Okay, not good at all. Okay. But if I repeat this process, what do I mean? Instead of picking one bulb at random, I pick multiple bulbs at random. What is the probability that, so I say I pick k bulbs at random? K bulbs at random. What is the probability that all the k bulbs I picked, so we are in this case, okay, again if I pick k bulbs at random, whatever bulbs I pick in this setting is going to be good. So I am surely going to accept it. In this setting, my idea is that if I find even one bulb bad, I will discard it. This is the whole bunch. Okay. The only way I will not catch this case is all the k bulbs turned out to be good. What is the probability of that happening? So what is the probability that all k bulbs, so they are all random bulbs by the way, are good under the condition that at least epsilon, at least 1% of the bulbs are bad. Under the condition that at least 1% is bad. Is it 0.1? Okay, 0.1. 0.1% is bad. So the first bulb is bad. So first bulb is good. What is the probability? It is 1 minus that object, correct? So this is the probability that the first one was good. Okay. Now I pick the second one. The second one was also randomly chosen. So probability that the second one is also good is also exactly this. Probability that both of them are good, since they are independent set things, so they are just product and just square. Product probability that both the bulbs are good. So similarly, probability that all the k bulbs are good. Yeah, someone asked me. So I would like to say that this is a bad setting, correct? This is when I would say that my algorithm has failed. When it has made k bulbs, couldn't find a single bad bulb, and actually there were a lot of bad bulbs there. So I would actually like to have this one less than 1 minus this, which is 0.01. So to pick some k such that this happens. Is it clear? So what kind of k will work? So in fact, if you take k to be something like, so if I put k to be 1 over this object, 1 over, so let me just put this to be 1 over 0.001, okay, then this quantity is exactly e, the 1 over e. Okay. So if I put it on top of that log of 1 over 0.01, then just convince yourself that this quantity is less than this. So basically, if I make log 1 over 0.01 by 0.001 number of bulbs, then my algorithm works. Okay. Now you might say that this is a huge number. Yes, it's a huge number, but it is independent of n. I started with n bulbs, and I have made just a constant number of bulb checks. So n can be millions, and I still have just made 100 queries. Okay. So this what I have told now. Is it fine with everybody? You think? So this is actually, in some sense, statistical sampling. Okay. So this is something has been there for ages and has been. So in property testing, we do exactly this, but we kind of push it to more combinatorial or algebraic objects. So let me give you. Yeah. So I'll write down some examples here, and we will try to remember these examples and then try to work on them. So the first example was what I did was basically this is, you can say that it is like testing of equality in some sense. So here is a string of b1 to bn, and I want to check whether the b1 to bn is all 1 or not, right? All 1 or far from being all 1. So that one was testing equality. Second one is actually something again which is very statistical. So in the IPL is going on. Now they want to, these people conducting the IPL or whoever they are interested, I mean, all the organizers and all, they want to check whether the demography of people who are following IPL has changed in the last 2 years. Okay. So in other words, they would say that okay, people between the age 0 and 15, maybe 75% of them are watching it last year. This year, is it also like that? Okay. Between say 15 and 25, say only say 25% are watching it. Maybe somehow this year has it changed or not? So this kind of stuff can be modeled in terms of distributions. So I have given two distributions, D1 and D2. Okay, so you can draw samples from them. So what do I mean by distribution? These are distribution on, just to make my life simple, let's it be distribution on 1 to n. Okay, it's a distribution of integers. I'm just writing it like this, but you can talk of any distribution. So I mean distribution on a finite set. So you can draw a random sample. A random sample. So if you draw a random sample, the random sample can be 1 with probability mu1, with 2 with probability mu2, with n with probability mu n. So the summation of them is equals to 1. And similarly, here also there is another distribution exactly on 1 to n. Now we are talking about distributions, okay? I want to check whether these distributions are similar or same, okay? Same, yeah, maybe I should give another example. Say the government has started a new project in a particular part of the country, okay? So some kind of this NREGA projects and all. And now they want to see that, okay, if the say 10,000 jobs have been given, now the 10,000 jobs should be given across all the political, people supporting various political parties. They would want to make sure, they want to now check whether this has been deviated from that thing or not. So is the distribution of people who have got the job, is it a uniform or not? So in other words, there is a distribution of on who has got what job, and I want to check whether it has been uniformly distributed. So D2 can be, say, uniform. So now here I want to check whether two distributions are same. Now I will come back to this one after some time, maybe, or maybe this. So here, one thing that we did was that if the number of if all the bulbs are good, we are accepting with probability 1, correct? Here we need not to be able to do that. Because we are drawing samples from distributions, two distributions can still be same, and still with some probability we might get some wrong set of samples. So here we want to distinguish between the case that, say, D1 is exactly equal to D2, or just like here we have defined farness, we have to define what is minimized farness here. Okay? So we want to distinguish between the case where, can someone give me any reasonable definition of farness here? I have two distributions. I want to talk about these distributions are same or far. What should be my definition of farness? So are people familiar with the L1 distance or any L2 distance, variation distance? There's so many different distances that are there between two distributions. So we can talk on that lines. So either D1 minus D2 in L1 distance is say 0, or I want to distinguish from the fact that D1 minus D2 in L2 distance is greater than, say, some epsilon. So this is a problem that we might want to answer. Very important problem that comes up all the time. So the third problem is actually most probably the first problem in property testing that was solved as part of property testing. So this is actually related to coding theory in some sense. So say someone gave you a function. Okay. So someone has given you a black box which contains a function, a big box which contains a function f, and has told you that the function, so this function is supposed to be is a function from, you can put in any number in any n-bit string, and it would output a 1 bit string, it's a Boolean function. And the person who has given it to me has guaranteed that, I mean not guaranteed, but he claims to have given me a linear function. Now what the linear function is? It's like he claims that for all x and y in 0, 1 to the n, if I take f of x plus f of y, now here plus is in the XOR bit, this should be equals to f of x XOR y, where XOR is in the bitwise XOR. And now I have been given this black box and I want to know whether this function, whatever I have been given, is actually a linear function or is far from a linear function. So in other words, I want to know, I will distinguish between the case that f is linear. Now I have to define the exact notion of farness again. Is f is far, meaning there can be many ways of defining f is far from linear. But the usual, one of the ways of defining it is that if I want to make this function linear, I must change f at a lot of places. I mean lot meaning an epsilon fraction of places. Or I would rather say another way of looking at it is that for all linear function g, if the number of x's such that f of x is not equal to g of x, this should be more than epsilon times 2 to the n. 2 to the n is the total number of values that function can take. So f from any linear function, or in other words the closest linear function in particular, must be off by at least epsilon fraction. Now you want to distinguish between these two cases. So can someone give me a algorithm that can help me do it? Okay, I mean I can evaluate a problem function at a random point x, but that doesn't tell me anything about whether the function is linear or not, right? Yeah, I mean it can be 0, it can be 1. I mean there's nothing that I mean at any single point it can be anything. Okay, choose x and y randomly and then excellent. So this is the one algorithm that is a kind of an obvious algorithm. Okay. Why it is obvious? Because if a function is not linear, and if you have to convince me that I have cheated you, I have given you a wrong non-linear function, you better end up showing me that see this is non-linear because here is an x, here is a y, and here is an x plus y, and which doesn't work. Okay. So the best hope is that let's randomly pick x and y, and we compute f of x. We not compute, but we ask the black box to give us f of x. You ask the black box to give us f of y. We ask the black box to give us f of x plus y. And if this plus this is not equal to this, then reject. And just like here, if you want to do it, maybe you want to repeat it multiple times, which is fine. Okay, this is an algorithm, but to prove that this one is working, you have to prove that, I mean, it is clear that it has a completeness structure. Now, completeness structure meaning it has this part of it in some sense, that if f is actually linear, I would never reject it, because whatever x and whatever y I pick up, this is true. It is not going to happen, correct? F of x plus, You have to somehow prove me that if f is far from linear, which is this setting, then I would catch this one with a reasonable probability. At least so that is, so I would like to claim something, some lemma like if f is epsilon far, according to this definition, okay, so this is epsilon far from linear, then probability that my algorithm rejects is at least some non-zero quantity, some constant quantity. It can be very small, 0.0001, like in this case. It was the case here. But then we can again repeat it constant number of times to boost up our error. So this is exactly where I think the main problem of property testing and in general statistical analysis differ. So this case setting, we were looking at linear properties, and although it had some statistical part to it, it had some linear properties to the level that this thing is not trivial at all. I will not be able to prove it right now. I can just give you a reference. If you guys are familiar with Fourier analysis, you can go and take a look at it, this paper. This is by, it's called Blum, Ruby, Rubenfeld. Loop, BLR. Yeah. Blum, Ruby, Rubenfeld. Okay. So this, algorithm is obvious, but the theorem, proving this theorem is not obvious. So let me just, so this is the part of the, so this is how actually most of property testing results goes in some sense. The algorithm is kind of obvious, and but analysis is not obvious. So I think now that I have only not much time left, maybe I should give the definition properly once at least. And so let me give the definition first, and then I will talk about another problem, which is what I started with, this G. Yeah, okay. So why is it called property? I mean, you can understand why it is called property. Property is basically because, I mean, we are testing of some input having something. Right? So the other way of defining it is that I have an universe U. Okay, this is an universe. I mean, this universe can be anything. Like in this case, it can be the case of all graphs. In this case, it can be the case of all functions. In this case, it can be the case of all distributions. So this is a complete universe U. I have a property P, which is a subset of U. Means this is the what according to my definition are good things. So in this case, in the graph, in the universe of all graphs, properties, all the graphs which are 3-colorable. So in this case, among the universe of all functions, property P is the class of only linear functions. Okay. And the idea is that for all, if I given an input x from the universe, okay, I want to come out with an algorithm A that does the following. What does it say? First one is, if x is in the property, then I want my algorithm to accept. So then probability that A accepts x, accepts meaning I should say maybe I mean, A output accepts, in some sense you can think of. A accepts. This should be, okay, it can be 1 or, so say if I say 1, let me just write down 1 for now. Okay. So if it is have the property, I want to accept it always. And if x is far from P, okay, what does far mean? Far means that if you have to change, so this is an input that is given x, correct? If you have to change the input at many places to make it have the property, okay, so which means that if for all y in this property, if the distance between x and y is greater than epsilon, okay, then you want to probability that it accepts is very small, rather it rejects is very high.
So distance is the Hamming distance?
It is usually the Hamming distance. Most of the time it is the Hamming distance. But I will come to that point exactly, because sometimes when we are talking about graphs and all, I mean, it finally boils down to how is the graph represented. But it's usually the Hamming distance that we are talking about. So I can in fact write Hamming. So are you familiar with Hamming distance, correct? Everybody? So this is of course the thing. Now we want to reduce something. What is it that we want to reduce? To begin with, we want to reduce, we want to optimize on something. Exactly. We wanted to reduce the number of times we look at the input in some sense, or number of bits we look at the input. Okay? So this algorithm, for this thing, what we define this notion called query complexity. Now a query complexity for A is the number of bits that of x that A queries or looks at. So A basically every time he had to look at what is the ith bit of x, he has to pay one rupee. Basically, how many times he has to pay 1 rupee is the question. Is the number of bits of x A has to query. I mean, of course, in the worst case setting, in the sense that the worst case for which this one happens, we are always in the worst case setting. So this is our definition of our algorithm. This is the definition of our property tester. This is the query complexity of a particular tester, and for a given problem, we would say that property query complexity of that problem is the query complexity of the best tester. For example, here this is the tester. This is one of the testers. I could have given lots of other testers. This is one of the testers, and the query complexity is constant. In fact, it is 3 here, correct? If I want to push it up to this one to be delta, so then I have to make some more queries. It will, of course, number of queries then I make. If you remember here, the number of queries I made was, of course, dependent on this delta that we are talking about and this epsilon that we are talking about. So query complexity can very well depend on epsilon, delta, and even n in some cases. The idea is that it should be as low as possible. We in general assume that delta and epsilon are some constants, so we don't really worry about that. We are more worried about getting rid of the n. Okay, so let me do another problem, and that is actually very.
You don't worry about the running time of the algorithm?
No, actually, when I started with, I told about the sublinear thing in terms of running time, but most of the time we don't care about the running time as such. We care about the number of queries made to the input. Now, that of course immediately imposes some amount of idea over the running time. If the queries made is constant, then running time has to be constant. Now, if the queries made is not constant, then things can just go off sometimes. There are some algorithms which has the problem, but the final idea is to understand the number of bits of the input I need to make an intelligent answer. That's it. Okay. So let me give you a. So I was talking about this distribution here, correct? Distribution problem. I will give you a problem which is like a toy problem, but related to distribution problem. Okay. So I give you a function f from n to n. Okay, means 1 to n to 1. Sorry, let me write that. Say from 1 to n to 1 to n. And somehow I have been guaranteed this promise that either the function f is 1 to 1, meaning for every I there exists a unique f of I and there is a unique f inverse of I. It's a 1 to 1 map, or it is 2 to 1, means two of them goes to 1. So basically here for all I, f inverse of I is 1, and for all I, f inverse of I is either 0 or 2. Some of them might not have anything, right? It is 2 to 1, it's a function. No, 2 to 1. So it's like two things goes to 1. I mean, so f of 1 can be equal to 3 and f of 2 can also be equal to 3. So it's like 2 to 1. And if I ask you that, okay, now here is this thing, function I have given you, distinguish between these two cases. Tell me which one is it. Is it this or this? Can you, I mean, of course you can do it. You can of course query f of 1, f of 2, f of 3, you can query f of n and you get the full answer. But do anybody have any, I mean, idea about how this can be done? No, that you cannot do. If you pick up one, that's a very good point. That's a very good point. If I could have done that, I would have done it in just one query. Yes, because at least I know that if I could have picked up one of them and I asked, okay, what are these inverse? I mean, if the inverses was 2 or 1, then I would have been done. But we don't have that. We have it, and only you can query here, take some point here, you can choose and ask what is f of I, and you get this way. So this is, sorry? Correct. So, good point again. So, if I have to convince, again, like you think about it that I have given you the f, and now you are trying to convince me that it is not 1 to 1. How do you convince me? You somehow hope that by some magic, you manage to find some I and j such that f of I is equals to f of j. And if you can find that I and j, then I am convinced now that f of I is equals to f of j, hence it cannot be 1 to 1, by the guarantee it must be 2 to 1. So I have to find I and j. Now this I and j can be anywhere, it's a random function, I mean it is some function, I have no idea how this function looks. So this is where it comes very similar to another concept in combinatorics is called, or combinatorics of probability, of birthday paradox. How many of you have seen birthday paradox again? Yeah. So birthday paradox basically says that if you pick here you can take it as an exercise, I will not prove it anyways, that here, if you pick something slightly bigger than square root n number of queries, then probability of finding at least 2 of them clashing, in this case 2 of them clashing, is high, at least some constant. Okay. So the algorithm basically would be pick some square root n i's, I mean square root n elements from the domain at random. You actually have to have a slightly bit more than square root n, maybe I will just put a log n there, square root n log n number of things at random. And now if you find any 2 of them now clashing in them, then great, you have proved to me that. Okay. If not, then you accept. And you have to prove that this will happen with, I mean, if it of course it is in if 1 to 1, you will never find a clash and hence you will always accept. If it is 2 to 1, you will find a clash with high probability. That is the kind of, at least the hope that you have. And prove it, and if you want to, you can take it as an maybe exercise to prove this. So now this is an example where the query complexity is not constant but is dependent on n. It is square root n log n. Okay. And this is also an example in which we can actually prove a lower bound. It is one of the few complexity areas where we can, just like we have been proving upper bounds most of the time. So we have, it is much easier to come up with algorithms, correct, which runs in times n cube. But it's hard to prove that it cannot go down less than n cube or something in time complexity or even in space complexity or something. But somehow in query complexity, proving lower bounds is slightly easier. For example, in this case, we can apply the same lemma that we are talking about, the birthday paradox. And the proof basically says that if you query slightly less than square root n number of queries, then with high probability you will not see a clash. So whatever the algorithm does, you make some queries. This f, I guarantee, is I make it a completely random function. I mean, just pick it and completely randomly permute it. So the algorithm has no idea about what is it going to make. So it basically only thing it looks at is queries some random objects, random elements in the domain. And but the paradox says that if you pick randomly square root n number of points, it will not clash with high probability. So this is an example where we have a basically a tight bound. I mean, upper bound of square root n log n, lower bound of square root n. Okay. Okay, now why did I pick this example? This example, try to convince yourself that this is actually a special case of the distribution thing. It's asking whether the distribution is uniform on 1 to n or half far from uniform, with a special guarantee that it is not only just far, but far by a different structure to it. Okay. Yeah. Okay. So in the next I will try to, in the next 15 minutes, I will try to prove this thing. So in the case of graphs, as you all know, the graph can be represented in multiple ways, correct? So the usual way of, so we have to define the notion of farness. I mean, that is what the approximate algorithm people solve. For us, it is not more than 3, but you will have to change the graph at a lot of places to make it have chromatic number 3. Okay. In other words, you have to remove a lot of edges to get the chromatic number down to 3.
It's the Hamming distance.
It's a Hamming distance in the adjacency matrix. Okay, it's exactly the Hamming distance in the adjacency matrix there. So here I mean that at least epsilon fraction of the bits of the matrix, adjacency matrix, has to be changed to make the graph three colorable. Okay. So let us consider the following problem. If the graph is very sparse, the graph has only say the graph is say not 3 colorable, it is say 20 colorable, but it just has a clique of size 20 sitting in a huge graph. Okay, n is huge, massive, but it has a clique of size 20 sitting there. So the chromatic number is of course 20. It's not 3 colorable, but the whole graph is also very sparse. What I mean is that if the graph is G is such that the number of edges in the graph is say n log n, something, right, much smaller than n. I mean the square, small o of n square. Okay. And G is not 3 colorable. So then, can we say that the graph is, then where does this graph stand here, rather I would say? The graph is not 3 colorable, but this graph is also not far from being 3 colorable, because since the number of edges is so small, I can just remove all the edges in fact. Okay. So this is actually the main crucial part of this new definition, that you have to assume the graph is dense. If the graph is not dense, then the answer is easy, because I don't have to answer that, because it is between here and where I am not even bound to give a correct answer. So this notion has to be exploited in some sense. So I have 10 more minutes, no? Can take some time. Okay. Okay, so I will not prove this one, but I will prove a 2 colorability. Okay. Now, what is 2 colorability? Bipartiteness. We will check for bipartiteness. Okay. So I want to check, given a graph G, I want to check is G bipartite. Or in other words, is G bipartite or it is epsilon far from bipartite in the Hamming distance of the adjacency matrix. Okay. So what does it mean by being epsilon far from bipartite? I can say that, so I have this graph G, correct? It says that if I partition into 2 parts in whatever way I want, of course there will be edges going across, which are always good edges, but there will be edges, so it's not bipartite, right? It's epsilon far from bipartite. So basically there must be edges which are violating edges, and more importantly, the number of violating edges has to be more than epsilon n squared. So when I say epsilon fraction of the bits, so number of bits in the adjacency matrix is of course n squared, correct? So it means they have to change epsilon n square number of bits. So here I have a graph G, I consider this bipartition. Okay. Now this bipartition, I mean this partition rather, is not a good thing because G is if G is the epsilon far from bipartite. So that means I have to change epsilon n square number of bits of the adjacency matrix to make it bipartite. That means that I have to change epsilon n square number of the edges. So in this case, if the number of edges that are inside each of these bipartition was less than epsilon n square, I could have just removed it and made it bipartite, which is not the case, correct? So the number of edges here has to be quite a lot, has to be epsilon n square. Now, okay, so I just gave this say that, so these are the, so if now say I give you a bipartite graph, I mean a graph, and I tell you that, okay, this is a prove me that whether it is a bipartite or it is far from bipartite. If it is far from bipartite, how will you convince me that it is far from bipartite? I have given you a graph and asked you that if it is not bipartite, convince me that it is far from bipartite. Or in other words, I am looking for a certificate of non-bipartiteness. Any odd cycle will do, a short odd cycle will be the best option, but odd cycle is the one, correct? If you can show me that, okay, here is an odd cycle, that's a certificate of non-bipartiteness, correct? So your best hope is to catch a odd cycle. That's one way of doing it, okay? Catch an odd cycle. The other option is bit weird. You give me a subgraph. You give me a subgraph of this graph. You have this graph G. You have looked at some edges and say that, okay, of course you have not looked at the whole graph, correct? You have looked at some subgraph of it. And say, let me move it here. Say you have given me that, okay, there is an edge here, there is an edge here, there is like this. Somehow you have given me a weird looking subgraph. I mean, not subgraph, rather sub-information of the graph in some sense. And you say that, okay, now this one proves that this is not bipartite. Why? Because I can try to find out a bipartition, and every bipartition, if it has a violating edge, then that bipartition is thrown out, correct? So if for every bipartition there exists a violating edge sitting there, then I am done. So basically, in other words, you give me a provide a say a set of edges which is a subset of the actual set of edges, such that for all partition V1, V2 of V, there exists some edge in E prime, there exists an edge E in E prime, such that either E is contained completely into V1 or in V2. So E is in completely V1 or E is in V2. I mean, so this basically means that both the ends are in V1, both the ends are in V2. This actually not. But if you think of it, it does turn out to be like that only. It's like what it means is that you are giving a big enough set. I mean, if it is not, if you don't have a cycle, then you will not be able to. It will have a cycle actually. But the reason I am telling it exactly in this way is that catching this one is slightly easier. Why? Say if I randomly pick up some edges. Okay. So I have no idea of the graph. I randomly pick up some edges. Now I know that this graph has a, so here is some bipartition of V1 to V1 and V2. Since the graph is far from bipartite, I am guaranteed that lots of edges are here. Epsilon n square edges are there. And thus, if I pick a random edge with probability epsilon, I would catch a violation here. So, a particular bipartition I can rule out with just constant number of edges. I mean, it's like a kind of, you can say, it's like a communication game that we are playing. I tell that, okay, here is a graph that so here is a graph that is bipartite. So you would ask me that, oh, okay, if it is so, what do you think is the bipartition? And okay, yeah, we have V1 and V2 is the bipartition. Then you said, then you random say sample. Now, if V1 and V2, if the graph is actually far from bipartite, then a random sample will catch a violating edge, and then you will say that no, see, V1 and V2 cannot be a violating edge because here is a violation. And then we can keep on playing this game until we exhaust all the possible bipartitions. Okay. This is actually the correct way of doing it, but the sad thing is that there is some catch here. Query complexity goes up badly because every time we have to use different random coins. We have to use randomly draw edge every time, correct? We cannot reuse randomness because we have to make sure that the independence is there. Okay. So the number of queries required is a constant times the possible way of bipartition, which is massive. So the way in which it goes, and I would most probably not solve it right now, it's not that hard, is that you first query a small set of edges, small subgraph, small set of edges. Okay. Now, if you have a small set of edges, that kind of tells you that, okay, now I have got a small information of the graph. Now, if this graph is bipartite, then the possible set of bipartitions that can be alive now shrinks drastically. And then you do this thing over there. I mean, if I start it will take some time, so I will not go it. I will tell you, if you are interested, you can go and possibly read this particular thing. But I would just want to make a particular comment here that there exists an algorithm which is actually this, that randomly query some edges, and as Arvind was pointing out, you will find a small odd cycle. Proving this is hard. Proving this is why we need this two-step thing. This way proving it is not the most obvious thing. The algorithm is that randomly query some small number of edges, small meaning constant number of edges, and you will catch a odd cycle with high probability. Okay. So the algorithm, let me just write down, is that randomly pick. So this is actually something like order of 1 over epsilon square edges, and with high probability you will get a odd cycle. So this kind of problems, so this basically proves that you can chase bipartiteness of a graph by looking at a constant fraction of the edges. So we were not trying to approximate in terms of understand what is this 4 colorable, 5 colorable, but if the guarantee is that it is far in the sense of Hamming distance of the adjacency matrix, then all we have to look at is a constant number of edges. And 3 colorable is exactly same as 2 colorable, except it is more complicated. The NP completeness and all doesn't come in the picture at all. It's not anything to do. It's actually a small click. You can, so basically this basically ends up proving that. So if not a small click, sorry, not a small click, but small subgraph that is not a 3 colorable. Just in this case, it is a small cycle that is not 2 colorable. small subgraphs. So in some sense, what this actually says in a combinatorial sense is that if a graph is epsilon far from bipartite, it must have a small cycle. Not only a small cycle, it will have a lot of small cycles because with random sampling we are catching it. So yeah, so just last statement. So currently our knowledge of property testing has it that we have characterized all the graph properties that can be tested with constant number of queries. It's not monotone. It is like any graph property that is invariant under induced subgraph can be tested in constant number of queries. In some sense, yeah, monotone is basically how we look at it, but it is induced subgraph can be tested in. So that is a famous paper of Alon and Shapira, and this uses some pretty non-trivial combinatorics from regularity lemma, which we cannot go into. So yeah, I think I will just stop here. So there is a survey by Danaron. She has written a nice survey, and that kind of starts the whole area. And for people who are more towards learning theory, in fact, I couldn't even go towards learning theory because I even didn't even touch the functional testing part that much. There is one of my collaborator, Eric Blias. He has written his PhD thesis, and that's actually pretty nice and compact. But maybe this Danaron's survey is the best one. There is some books on it, but yeah. There are lots of surveys online actually, but Danaron's I think is the most basic of them.